All right, so today we're going to talk specifically about Hess's Law. This is probably my favorite part of the unit. It's easy problem solving once you get the hang of it, and I think you'll actually not find it too bad. So let's talk about what it is first, and then once we've figured that out, we'll talk about the rules and we'll go through some examples. So the Hess's law is also known as the law of additivity of reaction enthalpies, which basically means that the enthalpy change of any process really depends only on the starting or beginning conditions, which are your reactants, and the end conditions, which are your products. So I want you to think back to Unit 2 when we did that flowchart of organic chemical reactions. It didn't really matter how you got to whatever I was asking you to get, as long as you got there properly. So if you took 3 steps or 5 steps or 10 steps, it really didn't matter. So this same process is going to apply here, except in this case, I'm going to actually give you all the steps. So if you take a look, if you look at this picture down at the bottom here, if state 1 are your reactants and state 2 are your products, it really doesn't matter how you get to the top of the mountain. You could take maybe a more steep path, or you could take a less steep path that's longer. But again, as long as you end up getting to the top and you get to your final products, you're doing okay. So that's sort of the premise behind Hess's law. For any chemical change made in several steps, the net enthalpy is actually equal to the sum, and that's where the law of additivity comes in, of your delta H values of the separate steps. So for example, there are actually many ways to get from solid carbon and oxygen to carbon dioxide. So there's the direct route, which involves taking solid carbon, burning it in oxygen, and making carbon dioxide. When you do that, it releases that much energy, 393 kilojoules for every mole of carbon that's burned. You could also do it with a less direct route, so it involves 2 steps. So the first step really involves using your carbon and oxygen and making what's called here atomic oxygen, okay? And then taking that, adding it to carbon, and making your carbon dioxide at the end. The cool thing about this is that when we look at this is that we can actually cancel stuff out. So each one of these steps has its own delta H value. But what we're going to do is we're going to cancel stuff that appears on your reactants and product side, kind of like what we did with spectator ions, and look and get a final equation. So in this case, I've got carbon on my reactants, carbon on my products. I can cancel that out. I've got atomic oxygen over here and atomic oxygen over there. Can cancel that out. What am I left with? Carbon, oxygen, carbon dioxide. Carbon and oxygen on my reactant side, carbon dioxide on my product side. So my equation ends up being the same. So how does that apply to my enthalpies? Well, basically, if I take these two and I add them together, I get the exact same number that I did for the direct route. So we're actually going to manipulate equations, cancel stuff out, and then add up our enthalpy values to get the final enthalpy of whichever reaction we're dealing with. So, predicting delta H using Hess's law. Hess's law may be used when the molar enthalpy may not be determined or measured using calorimetry. So sometimes either the reaction is too complicated, it releases too much energy, or for whatever reason we can't actually do a reaction in one step in a calorimeter. But if you can do the intermediate steps or through 2 or more equations, then what we can do is we can calculate the enthalpy of those and make our new target equation. So what I want you to realize here is I've got a new term for you, a target equation. That's basically our final equation that we are looking at. And then if you can get to your target equation, really all you have to do is add up the enthalpies and get your final enthalpy that you're looking for. While you're doing this, 2 rules to remember. Please highlight this or start in your notebooks. Rule number 1, when you reverse an equation, you need to change the sign of a delta H. So if you change your products and reactants and flip them, you multiply your delta H by -1. You have to change the sign. The second rule, if you multiply the coefficients in an equation, you also need to multiply your enthalpy change by that same number. So let's go through an example. Oh, shoot. Don't look at that. So we're going to go through an example, and I'll talk you through it. So to calculate delta H for this equation up here, so this is actually your target equation. Okay? And I give you the intermediate steps, which is really nice of me, so you don't have to figure this out on your own. So here's equation 1 and here's equation 2. So the first thing I look at is what's in my target equation and what's in the equations that I'm given. So in this case, for my target, I need to have solid sulfur on my reactant side, and I need to have SO3 on my product side. If I look at what's given to me, here's an equation. I've got solid sulfur on my product side, or reactant side, sorry, and I have sulfur trioxide on my product side. So that's looking actually pretty good. But I've got these extra things in here. What can I cancel out to get to my target equation? Well, in both cases, this SO2, you don't see it anywhere in your target equation. So I know I'm going to have to, somewhere along the lines, cancel out that SO2. And it works out really well in this case because I've got SO2 on the reactants, SO2 on the products. They cancel each other out. So when I actually add up these two equations, what am I left with? Well, I have solid sulfur. I have 1 oxygen plus another half of oxygen. So I actually have 3 halves of oxygen gas. And on my product side now, all I'm left with is my sulfur trioxide gas. So I didn't really have to do any manipulation of equations. I just had to cancel some stuff out, and I actually got my target equation. Yay! So what that means now is I can basically, to find my target enthalpy change, well, all I have to do is add these two up. So I'm just going to take my delta H1 plus my delta H2 and punch in my numbers. Negative 75.2 kilojoules. And when I punch those two numbers into my calculator, I get minus 395.7 kilojoules. Done. So that's basically how Hess's law works. So if you can cancel things out to get to your target equation, all you really have to do is add up your delta H values. All right, so let's go to this exact same example, but it's represented with an enthalpy diagram. You will have to either interpret or draw an enthalpy diagram on your test and on your exam, so make sure you know how to do this. So all it's saying here is here are your reactants, and down here are your products. This was your intermediate step right here. And all it's saying is to get to that first step required this amount of energy. To get to that second step required that amount of energy. To do the whole thing, 395.7 kilojoules of energy was released. So we basically add up my two enthalpy values. It also represents an exothermic reaction because you have a lot more energy stored up in your reactants than you do in your products. So where did that extra energy go? It was actually released in the form of heat. Okay, so one more example. Oh, I thought this would happen. So I'll just erase this really quick. Sorry, I thought I had done that before I started the video. So here's one that's going to be a little bit more complicated, so we'll talk it through. So using Hess's law, find the enthalpy change for this reaction. So again, whatever I give you here, that's your target reaction. That's what you're aiming for. Now what we have to do is manipulate the other two equations that I gave you to add them up and get to that target equation. So there's multiple ways you can look at doing this. So I don't know, you can start by looking at what needs to be canceled out. You can start by looking at what's on your reactant side of your target, what's on your product side of your target, whatever you'd like to do. So I take a look first off at equation number 1, and I look at my methane and my water, and I see that I'm short by about half. So in my target equation, I have double the amount of methane, I have more oxygen, and I have double the amount of water. So my oxygen's a little bit concerning to me, but something might happen to kind of make that work out. So I'm just going to ignore it for now. But I do know that in order to get to my target equation, I have to multiply both of these values by 2. So this is sort of the second rule that I taught you. What I'm going to do is I'm going to take equation number 1, and I'm going to times the whole thing by 2. So I'm going to have 2 CH4 instead of just 1. I'm going to have 4 O2s, and it's going to make 2 CO2s and 2 H2Os. Oh, sorry, no, 4 H2Os. Didn't multiply that one. 4H2O. Awesome. So now I'm not dealing with this reaction anymore. I'm just going to cross that whole thing out. But that's a lot closer to what my target is. What do I do to my delta H value? I also have to take that value and multiply it by 2. So I have to take my negative 890 and multiply it by 2. So don't forget to times this by 2. Whatever you do to the equation, you have to also do to the enthalpy value. So you end up with 1780 kilojoules. Oh, sorry, and it's still negative. All right, let's check out equation number 2. I'm actually going to do that in a different color just to keep it separate for you. So I'll do this one in blue. All right, so in equation number 2, if you look, I've got carbon monoxide on my reactant side. But in my target equation, I have carbon monoxide on the products. So I'm going to have to flip this equation to make things work out. So when I flip it, I'm basically going to write the reactants on the product side. So I write 2CO2 on my products and O2 on my products. And I'm going to write the products on the reactant side. So the 2CO2 that was initially over here goes into my reactants. So all I've done is I've just flipped the equation. When I do that, my rule for delta H, I have to flip the sign. So instead of negative 566, it is now positive 566 kilojoules. All right, great. So now let's see what I've got. Can I add this up, cancel stuff out, and get to my target equation? So let's see. Well, I can cancel out really. Oh, what did I do? I messed something up here. Oh, sorry. I wrote CO2 here, and it should just be CO. There. So I can cancel out right now. I've got CO2 over here on my reactant side, CO2 there on my product side, so that cancels out. And I can actually cancel out one of my oxygens because I've got one oxygen here and an oxygen here, but I'm not going to cancel all the oxygen. I'm just going to cancel one, so I'm left with 3. And hey, if you take a look at that, that actually ends up being your target equation, so I've done it. So what's my target? 2CH4 plus 3O2 gives you 2CO and 4H2O. So check. I've gotten to my target equation. Now that means all I have to do is add up these two values of delta H, and you're good to go. So when you do that, you should get that your delta H value is negative 1214 kilojoules. And that's it. So if you get that, we'll do a lot more examples in class, and hopefully that will help you out. One last thing before we stop the video is now you're going to be expected to do some multi-step energy calculations. So that basically means that you might have to do a Q equals MC delta T, an enthalpy change where you're calculating the molar enthalpy, and Hess's Law all in one problem. That's going to be the challenge, is solving those types of problems. So we will go through some examples of that together.